Good morning, everybody. And today I will have an extra session on the LL parsing and LR parsing. I try to finish the chapter 2 for this week. Let's get started. I just make sure that our recording is in session. So okay, right here, let's get started with LL parsing. First, to enable the LL parsing, we need to write a LL grammar. And LL grammar, we have this LL family grammar with number K. The K is the level of the look ahead level. And the rightmost derivation, that leftmost derivation is this second L. The first L is left to right. Let me check whether we have the sharing. Okay. I'm just trying to check the video level and the microphone level. And when designing a recursive distant parser, one has to acquire a certain facility in writing and modifying L1 grammar. So basically, you need to implement the LL1 grammar using the recursive distant parser. So if your grammar is not LL1, basically this recursive distant parser cannot be done. So that's very important. So the two common obstacles to LL1ness are left recursion and common prefix. Transformation of a grammar from non-LL1 to LL1 need this elimination of left recursion and left factorization. And let's go. Left recursion. Left recursion is very apparent. If you have one non-terminal on the left and on its right-hand side, you immediately have itself. This is called the left recursion. Left recursion is bad for LL grammar, but it's good for LR parser, and we will mention about this later. A grammar is said to be left recursive if there is a non-terminal A such that A will derive A right away and with alpha or something follow it. Anything that have leading non-terminal, like both on right-hand side and left-hand side, that is a left recursion. The trivial case occurs when the first symbol on the right-hand side of a production rule is the same with the symbol on the left-hand side. The following grammar cannot be parsed top-down. The reason is if you parse down from top-down, that would be from left side to right side. Then you will find this. Then you will call this same rule again. Now we'll go into here, and then you will call left side again, and this one will never end because it is always the first choice. If it is buttoned up, you from the right-hand side, you have everything ready, you actually reduce to the left-hand side, then this one is okay because there is no confusion or no ambiguity. Elimination of left recursion. On the left-hand side, we have left recursion. Right-hand side, we have right recursion. And if we have the same input token, we have ID, comma, ID, comma, ID, comma, and then with several ID, comma. And this way, in the left recursion way, we actually have a pair of the, we actually first have we have the ID followed by a comma. So we check the ID followed by a comma, and then we have another ID followed by a comma, something like that. This is called the left recursion. And if we cut it by ID first, and then comma ID. This is right recursion. And this semicolon is the end of the sentence. So, and by doing this, actually you just transform the left recursion to right recursion. And for this ID, this example, you just need to isolate the first ID and follow by comma ID. Then it will be broken. For the left recursion will be transformed to right recursion. Common prefix. Common prefix occurs when two different production rules with the same left-hand side begin with the same symbol or symbols. So in this situation, we have ambiguity. Anything with ambiguity, when you go top down, you are not able to decide which rule to pick. Then that will create trouble. Both left-hand side, both left recursion and common prefix can be removed by a grammar mechanically. And this left factorization is something like this. You have the common left factor, then we can actually extract it out over here. And then you actually put the expression and the argument list that is in two rules with a vertical bar, so that you actually put it like statement list tail and have a new non-terminal statement list tail because they share the same head. So we put the both statement, both right-hand side into a vertical bar. So actually, effectively, this one actually add one more rule. So here, actually, if you don't use a vertical bar, here should be a statement list underline tail, go to argument list, parentheses over here. So that actually add one rule and add one non-terminal. And if you look at if we just conceptually look at it, it will be original case is you have this, and then now you put A over here, and then we add one non-terminal B, and then have such a rule. This is similar to when you are dealing with math. You have A times B plus A times C. Then by the associativity, you get the A out, then you get A times parentheses. And then inside the parentheses, you put B plus C, something like that. So that's called, actually, this is called left factorization. And that eliminates the left recursion and common prefix, does not make a grammar LL. So only by doing these two things doesn't make it LL language in a strict sense, because you still may somehow fall into that recursion or ambiguity. And there are infinitely many non-LL languages, and the mechanical transformation work on them just fine. And the few that arise in practice can generally be handled by heuristic. So if there are certain problems getting out, then we actually can always by heuristic. We always can remove them by heuristic. That means there are several cases that are not handled by systematical way of doing things, but we can always finding out a smart way to remove them and handle them for LL language. Parsing a dangling else. The best known example of not quite LL construct arise in language like Pascal, and in fact for many languages as well, like C or even Java has the same problem, but they are handled, in which else part of an if statement is optional. The natural grammar fragment for the if statement is like this. A statement, you can go to if condition, then clause, and then else clause. So this is if condition, then, and then else. For the then clause, you have then clause go to then and one statement over here. An else clause, you can go to else statement or an empty string. So none else, nothing in the else clause is also okay. Then this kind of grammar will cause a problem because it allows the else in such a statement. You have if C, if C1, that's condition 1. Then if C2, that's condition 2. Then S1, that's statement 1. Else S2. This will cause problem because you don't know this else belong to this if or this if. So you don't know which one it pair to. Then it creates trouble. We need to handle this situation. It is called the parsing in a dangling else. So removal of dangling else is number one solution is we can have separate balanced statement and unbalanced statement. For balanced statement, you have both then and else. And then you put a if condition, then balanced statement, else balanced statement. And by doing this, you will be able to make sure if it is a balanced statement, it will be there. Otherwise, you have unbalanced statement if the condition, then statement, if condition, then balanced statement, else unbalanced statement. What this means is actually this rule is written above this, so this will be checked first. So balanced statement come first. So you pass from here, this one will be handled first. Then this one will be grouping together first before it check this unbalanced statement. But if we only have one production rule, then we cannot differentiate it. So right here, we invented one more statement, and then we allow this balanced statement to be checked first. That will break the dangling, that will remove the dangling else. The fact that else clause go to else statement come before else clause go to empty string. That's the way we try to handle. And this is in this balanced statement, and this is in the unbalanced statement. End up pairing the else with the nearest then as desired. Removal of ambiguity. The usual approach, whether top-down or bottom-up, is to use the ambiguous grammar together and with a disambiguating rule that says else go with the closest then, or more generally, the first of the two possible production is the one to predict. And actually, this is just describing the previous slides. So let's go on. M marker for structure statement. So there is another way we can finish it. It's like you add one n markers so that you know where the clause end. So let's look at it. This actually for this Argo family modular 2, modular, and operon all have this. And okay, then C language we use the braces, left brace and right brace. That's the same meaning. But C language, of course, also had the dangling else problem, but the compiler already handled it by the grammar. So, and another way to handle it is adding the statement, the keyword of else if, and adding the n marker can help to remove the dangling else. But the problem that it arises is with the n marker, then this if then else, and then if we have nested if then else, then it will become something like this. You will end up with many end in one statement. So if we there is a need for this else if statement, then it will look like this. Then it will remove several end marker, and the original if then else will create ambiguous. So this is how the second way of handling the dangling else problem. Let me check if there's any question or anybody come in already. Okay, now we have Gail. Let me say hello to him. Okay. Any quick question so far? Okay, then we will continue the second talk. The second lecture on this LL parsing, we will look at the table-driven top-down parser. Remember that in the general discussion for parsing, we already covered the recursive descent algorithm. Right now, we talk about the table-driven top-down parser for LL parsing. Excuse me for the water. This table-driven top-down parser probably is the most complicated parser in all of the parser being mentioned in chapter 2. So be careful. This one is really very bizarre and very confusing. And it is table-driven, so we need to have one table, and the table is constructed by the EPS. There is a set, and there is another set called first set, predict set, and follow set. And these sets are created for the prediction of the parser. So actually, this table-driven top-down parser is a predictive based. Let me go back to the previous slides. Let me check. There is one slide about. In the parser family, let me try to find out the parser family. It's on the overview part. Okay, right here. Remember that we have the recursive descent, and then if it is pure recursive descent, it would require the backtracking. That's the recursive descent algorithm we talk about. But right now we are talking about this LL parser. That's general LL1, LL2, LLK parser. That's predictive based parser. So right now we are talking about this parser, not the previous one. Previous one is more easier. But this one, since it is predictive, so you can handle higher level LLK language or grammar. So that's what we are talking about right now. So it is a little bit more complicated. And it requires to calculate this four set. And this four set is for prediction of what are the coming token and whether it follow the grammar or not. So table-driven LL parsing, you have a big loop in which you repeatedly look up an action in a two-dimensional table based on current leftmost non-terminal and the current input token. So it is based on the non-terminal and token. It's different from YAC or Python we saw that last session. It is actually on current status and the current token. This one is current non-terminal, or you can call it current production rule, because every production rule we have one left-hand side. So current leftmost non-terminal. Oh, I'm sorry, this one is current leftmost terminal. So it's the first one on the right hand side. I'm sorry, I described it wrong. It's the first one in your right hand side and your current input token. So if you move on to the second non-terminal, then you would need to use the second non-terminal. That is the one we are using, and current input token. And the action are matching a terminal or predict a production. All three announce a syntax error. This is actually if you have the when we go down to the recursive descent algorithm, we see a integer, then we match that terminal, the number, that's number one. Second, if we see a parenthesis, then we may predict a parenthesis and then expression, and then parenthesis dual, and then that is the prediction of a production. So based on the non-terminal, leftmost non-terminal and current input token to determine these three things. Either you apply a rule, or you apply a prediction of the rule, or you match a terminal, or you cause a syntax error. So table, driver and table for top-down parsing. In recursive descent parser, each arm of a case statement corresponds to a production and contains parsing routine and the match calls corresponding to the symbol on the right-hand side. So remember, this is in the recursive descent parser, it's quite easy. You just actually match the subroutine and the token. Let's go back to last slide. And we need to review it a little bit. Okay, right here. Remember this one? We have one rule, then we have the left-hand side, we put it right here. It would be a procedure. And on the right-hand side, if we see some input tokens, the input token, the first one is statement. So it's possible input token would be, the first one can be ID, read, or write by this statement. Then it will call the subroutine statement list. Or if it is the end of program, you will skip the epsilon production. So this one is in the recursive procedure for each terminal. And then you will go down one level. You know, this is the last time we talked about this. And then let's go back right here. And that's the way it passed. It contains the parsing routine and the match cells. Okay. So at any time and at any point, a given point in the past, if we consider the code beyond the program counter in the parsing routine invocation, currently in the code stack, we obtain a list of the symbol that parser is expected to see between here and the end of the program. So basically, that's talking about right here. That's talking about this list, the ID, read, and write. You need to know about what token are you expecting. And this is the prediction we talk about. But right here, recursive procedures, you can just determine by yourself. But in table-driven, you need to put those prediction set into your table. So that's what the need is. And a table-driven top-down parser maintains an explicit stack containing the list of symbols. So actually, you will create a stack that put in all of the symbol for prediction. And in the recursive descent parser that we talked about before, that actually is put, those symbols are in the subroutine. But right here, we put into some stack. So right here, we put into some stack. So in our driver and parser, actually that will put into certain stack. Sorry, this part is a little bit complicated, so I need to go back and forth for different slides. So right now, let's look at this table-driven LL1 parser algorithm. The code is a language independent. So right here is a pseudocode, not dependent, not for any language. And it requires a language dependent parsing table. So the table need to be created. So later we will create a table for figure 2.20, and for the language 2.16. 2.16 is the calculator grammar, and we will create a table for it. So right here, let's read it. You have the number of terminal number or non-terminal number of a symbol in your language, and then you have the production rule. So here define several things for the language. You can call it as a grammar. So, and you can think about that these things actually are the tokens and the tokens and an ID and the production rule that you actually, just like you use the YAC or you use the next program, and actually those things are specified in your BNF or in your regular expression, and those things will be when you design the parser ad hoc by yourself. Actually, those things need to be described in your program. And then you have a parse table, and this parse table contains non-terminal and terminal. Terminal is the symbol, so you use these things, non-terminal and terminal, and put in the action for prediction, what the prediction you have, or it is an error, and also put in your production rule. We will talk about this later. Anyway, and then you have the parser stack. Those stacks are used to put in those symbols for prediction and what will be the next token you will be seeing. Then you will have the function called parse stack push. Then you will push in those symbols. And then you have a loop. Each time you process a loop from the parse stack, you pop out one symbol, and then the symbol being assigned to symbol, and then it is the expected symbol. You see that whether it's a terminal, if it is a terminal, then you try to match that symbol. Otherwise, you will check if it is the end of the program. If it is the end of the program, then we finish. So this one, the match of the expected symbol is similar to this one. You try to match the ID because you call one body, but you try to match the ID. If it is matched, then we know that it's a ID or symbol over there. But right now, the recursive one with table, with the table, then you would use the table to find out a symbol to check. And that's from the code stack. So we are in right here. And then if it is non-terminal, then we use the, and if it is not this if it is not a terminal and it's not the end of program, when we will come here to check if the input token, the next token is the same with the expected symbol from your parse table. So you will look at the expected symbol and the input token, and then try to find out if that token and expected symbol from this table is its action an error or not. If it is an error, then you will create parse error. That means the current input token is not expected. It's not what you want. It's not what you predicted from your production rule. Then you create a parse error. Otherwise, you would go, because that symbol is a non-terminal, so non-terminal, and then you see a right token on the next symbol, the token is correct, then you would actually find a production rule. Let's go back. What this actually means is right here. let me show you the previous slides. When we provide an example, we try to, at this moment, we try to check currently is a token of the parenthesis, and we try to check is the next one is a expected integer or not. If it is not an integer, then actually we will actually call it an error. So that's what it is. But it is put into the table format. But right now it's put into the table format. And if it is the expected token, but it's non-terminal, then we bring in a new rule. And in new rule, we push in all of the symbol into the step. That means we go down one level in the recursive descent algorithm to check one more symbols, and we push all the symbol into there. Those symbols are predict set of the table. It's not the one from input token. These symbols are the prediction set, and we will talk about prediction set later. So the table look like this. You have program, and that's your symbol, your non-terminal ID, and here 111. These are the predict table, the symbol, and this -1 are the error tokens. Let's go back. The -1 is this action error token. So at this point, probably everybody are lost because this actually doesn't know what it's talking about. The textbook is somewhat confusing. So up to this point, probably you just overwhelmed, doesn't know what it's talking about. Anyway, table-driven parse of the sum and average program, the parser iterates through around a loop in which it pops the top symbol of stack and perform the following action. If the pop symbol is a terminal, then the parser attempt to match it. So we talk about it to match the ID or the read, okay? And against the incoming token from the scanner. If match fail, the parser announces a syntax error that we talked about it already, and otherwise initiate some sort of error recovery. If the pop-up symbol is a non-terminal, then the parser that will use that non-terminal together with the next available token to index into the two-dimensional table that tells it which production to predict. So this blue, red, green. Blue, red, green actually means the blue, red, green right here. So that's what it says. To handle the three things, the terminal, non-terminal, and the failed cases. So the whole sum and average program will go into such a way to produce a parse tree like this. And these are the detailed steps. It will do initial step content, and then predict this rule, and then predict second rule, and match read. So actually, it is checking certain read. For example, initially the first statement is read. Oh, I'm sorry. Let me try to find the sum and average program. Sum and average. One moment, please. Sum and average over here. Oh, this is the sum and average. So the sum and average program is example 2.24. So the first statement you actually have read A, read B, and then A plus B to the sum, and then write sum, and then write sum divided by 2. This is the sum and average. That's in example 2.24. So actually, that read A and read B stuff is the sum and average. So initially, you started from the program, this rule, program, and program will go to statement and end of program, and statement list will go to statement and the statement list, and the statement will go to read ID. So first one, you go down, 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 and read ID. Try to match whether it's read ID or not. And during these 4 different statements, initially you have a content, as initial stack content, and then you find a rule to predict, okay, right now we are trying this program statement $$ rule, okay, and then if the predict set still matching, then you actually go down one more level, okay, I try this statement list, and then statement list, and trying to check whether the expected symbol is read. Okay, read is okay, then we go down one more level to predict statement and read ID, is that true? Yeah, and then we go down one more level to match whether read is a read. Okay, we match. Then we match the second one, whether it's a ID or not. Okay, A is an ID, then we finish the match. So this is how the read A being verified, and then read B being verified using the predictive table, and then one by one construct such a parse tree. But this is still very confusing anyway. Let's look at the example. So trace of the parsing process. When you read this, keep track of the leftmost non-terminal. You push the as yet seen portion of the production onto a stack. And then the key thing is to keep in mind that the stack contains all stuff you expect to see between now and the end of the program. So you actually try to find out the predict set and check whether it's valid or not. So what you predict is something you will see. Now let's look at how to, so because it's prediction based, so the prediction set is very important. So right here, let's look at how to build a prediction set. Otherwise, it's quite hard to understand what this program is talking about. So the whole idea is like, from a language, you always find out the prediction set for a non-terminal, and then use that non-terminal, because non-terminal usually is a left-hand side, so it is representing one rule. So we basically use that non-terminal to find out what are the symbols or tokens I may see for the next one. So we look ahead for one symbol to see whether that symbol is what I wanted. If yes, that means my current rule is valid rule, so I don't need to change other rule. And then I check the rest of the symbol to make sure that my rule is actually the one that we need in our parsing process. And then if not, I will go down, and then if not, I will complain the error. If yes, I will finish that, and then maybe go back to find another rule to check. So the whole algorithm is recursive descent, but you actually always check in the predict set. So now we'll tell you how to build a predict set for the calculator language. The algorithm to build a predict set is very tedious, so actually it's quite hard for a real size grammar, but relatively simple. It is tedious, but it is simple. Why it is tedious but simple? Simple means you can just actually use a mechanical way to do it. So it's very mechanical operation. It consists of 3 stages. First, compute the first set of the symbol. Second, compute the follow set of the non-terminals. 3, compute the prefix set or table for all productions. So you actually compute first set, follow set, and prefix set. And what that is means? Okay, we look at what is said later. Set definition. Given a context-free grammar in BNF format, so a grammar, we can construct the following set. So for each non-terminal, which A is a non-terminal, and you can think about this as one rule, okay? For each rule, we can have the first set, follow set, and prefix set. That's what the previous slide said for every non-terminal in the language. And there is another set called empty production rule set. And this empty production rule set, EPS, for all non-terminals that could expand to epsilon string. So that's what any non-terminal or any rule that will expand to epsilon. So for example, that a program that had no code at all, so that program can be an empty string. So that's so the program non-terminal is considered a element in this EPS. Or I have a statement, and that statement actually is empty. Then it can be a EPS. So this set of non-terminals are non-terminals that has no content. That is what it is. And then any non-terminal that has 3 sets. The first set is the first set, the set of token that could appear as the first token in expansion of A. What this means, this first set. So the first set is actually right here. So we have the statement list, right? This is non-terminal. And this statement list will go to statement go to here. So statement list first set will be ID, read, and write. These 3 are the first set for this statement list. And same thing for statement, since statement is the first one in here. So statement's first set is also ID, read, and write. These 3 are also the first set for statement. So these are the first tokens that you will see. That is called the first set. Oh, I'm sorry, that's the previous one. So that's the first set. And second one is follow set. Follow set is the set of tokens that could appear immediately after A in a expansion of S, the starting symbol. So what this actually means, that's the follow set. What is a follow set? Follow set means, for example, I have, let me see, I have a ID, right? And I am actually, say, okay, this one is not a good example. Let me try to find a better example. Now we are talking about a follow set. I need to try to find a good example for follow set. And the follow set actually just need a simple arithmetic equation. Okay, it's hard to find an example. Anyway, let me go back. So right here, let's talk about a follow set. Say if I have expression plus expression, right? you may A plus B, have A plus B. So the first expression will go down to a term, and the term will go down to a factor. Factor will go down to A ID, right? And that A ID will actually represent an expression that's used in our YAC. We have that expression plus expression situation. So the token plus or the token minus in the YAC rule that we use as an example, that two token is considered a follow set. So that means that I have an expression, and following expression, I can have a plus sign, minus sign, and also maybe multiplication sign or division sign. These four tokens are considered the follow set for the non-terminal expression. Okay, the first set is the one that would appear when you expand A. The second one are the tokens that will follow you but not included in you. That's the first set. The third one, predict set, is the set of tokens that could appear next in a valid parser string in the language when the next non-terminal in the parse tree is A. And this one is actually like, this one is actually, let me see, this one is actually the predict set that we want. That means the predict set actually is, okay, I have the program, this is non-terminal, right? But what is the first token I'm going to see? This ID read and write is in the predict set. So this non-terminal and the ID read and write maybe no relationship, is not following it. It is maybe not maybe is and maybe not in its expansion, but the first token I'm going to see, that's my predict set. Okay. So let's look at this three set again. This is quite important. The first set is the one that when I expand, I will see it. The second one is the one that immediately follow me. The third one is that when I parse it, somehow when the non-terminal in the parse tree of A, I will predict it, something that I will see. Maybe it's a follow, maybe it's a first. So the first token I will see is predict. And this predict is the most important because our parser is built on predict. Our parser actually built on predict. So whenever we start to parse the program, actually we just want to see what is the next ID I'm going to see. So the whole table driven for LL family is trying to find, am I seeing the right next token or not? So that's why we try to calculate this EPS first and follow and predict set. And right here is a mathematical definition. So this one, I believe nobody would like to look at it. It's so bizarre. Nobody know it. We just skip it. So do we need to calculate the first set in the parsing? Actually, top down, probably you don't need that. It's very obvious. The first set is the set that has the token that when you expand. So pretty much you just trace down the tree, you will find out the first set. So basically, like the following discussion, we won't discuss first. We will just discuss empty production symbols and set, and then predict set and follow set. EPS, empty production set, and or maybe you can also call it epsilon production set. Empty and epsilon is the same word. Okay. Definition: EPS contain all non-terminal that could expand to empty set. So this EPS has two things. First, in your grammar rule, if the non-terminal that has an epsilon production, then this non-terminal is belonging to this empty production set. Or any non-terminal that has a production, and that production only contain the non-terminal that are all in EPS. So actually, for example, I have the statement list, and then I only have one production rule statement, and then statement only contain only the empty string. So then the statement list is the non-terminal, something like that. So these are the two rules to check whether empty production set is defined. How can we find them? Second one, the predict set. Predict set definition, the predict set of A contain all tokens that could appear next on the token string when we expecting A. When we expecting a non-terminal, and what kind of token will we see? Okay, so prediction set of A contains any token that appear as the leftmost symbol in the production duo of A. Okay, and then second rule, for every non-terminal B that appear as the leftmost symbol in a production duo of A, every token in prediction set B will be the prediction set of A. Okay, so if A belonging to the empty production set, every token in follow set of A will be the predict set of A. Okay, these are the three rules, and this is hard to understand. Okay, forget it. Now let's look at this example. It's easier. The rule one actually say this: any token that appear the leftmost symbol in the production rule A. So if I have an A production rule, A go to token, then this token should be included in the predict set of A. So this is easier to understand than this. So if I have rule, say I have this statement, and statement go to read ID, and then read ID, the read will be the token that I will see on the leftmost symbol. Then I include the predict set A, include that token. So this plus equal means to append that into my set. Second one, if I had a non-terminal B, the leftmost non-terminal, if my production rule has a non-terminal and that one has a predict set, then all of the token in the predict set will be my predict set. What this means, actually, if I have a set, a non-terminal, say I have a statement, right? And I have a statement list. A is the statement list, B is a statement. So anything B predicts, say read and write and ID, okay, and then that one is my predict set as well. So that's what we actually observe. For the program, statement list and the statement all have the same predict set. Okay. Then the third one, if I am the empty set, then anything I follow is my predict set. What does it mean? My cell will go to an empty set. So I have an A, then I'm followed by a certain symbols. So the first token I'm going to see is something behind me. Something behind me will be my follow set. And my follow set actually is the token I'm going to see if I am empty. I have nothing, right? So anything follow me will be anything I will see first. So that's the three rules we have for predict set. And then for follow set of a non-terminal contain all the tokens that could come right after A is a very pass. Follow set of A contain any token that immediately follow A on the right, on any right-hand side of a production rule. For any non-terminal B that immediately follow A on any right-hand side of a production duo, every token in predict B will be the follow set of my non-terminal A. For any non-terminal B such that A appear rightmost in the right-hand side of a production duo B, every token in the follow set of B will be part of my follow set A. Okay, anyway, I read this very fast because it's hard to understand. Let's look at this example. If there is a production duo, the left-hand side is C, and then I'm here, my set A here. Some token just immediately follow me, say I have the expression plus expression. So that token plus is my follow set. It right follow me, okay? And then second duo right here, right? If I and myself and the next non-terminal is right here, so anything that B predict means that B will C. Something B will C is right after me, so that is my follow set. So I include it. Third one is if I have a duo that I am the rightmost element in B's production duo, so that anything B follow, I will follow. Why? Because I'm his last one. So whatever follow him will be my follow because I'm his last one. So everything behind inside this production duo that B follow, I will follow. So these are the three duos. So remember this production duo, whatever I wrote down right here, these are more important than this duo. It's hard to understand anyway. Let me check whether Miguel is still alive or not. I'm not sure he knows it. Okay. How is the sets so far? Okay. He's still alive. Let's continue. Now let's build a prediction set and the follow set, all kind of sets. Now let's look at one example. This one is slightly different from the calculator grammar that we see in textbook, but it's quite a good example. S is the starting symbol, EXP is the expression, ERM is the terminal, EXP tail is the expression tail, OPA is the addition operator, so it's a plus minus sign, and then S factor is a factor, so it could be the operator plus factor, so it could be plus sign with factor, so it's a partial factor, and then factor would be a number or a left-hand side parenthesis expression right-hand side. So this can be integer or an expression with parentheses. So that's a factor, and this one is a factor or a factor with a plus sign. So this could be some part of the tail for a terminal for a term. So these are something, because the LL grammar usually is not very elegant, so you really cannot read it too much. Anyway, we based on this set of the grammar, that's LL1 grammar. Let's look at how to build a prediction set and the follow set. So to calculate the prediction set for that language, for that grammar, first we need to find out what is the epsilon production set or empty production set. So the rule is to construct EPS, we just use rule 1, any non-terminal that generate to empty string. So right here we have 2. So this expression tail and terminal tail, these 2 are in the EPS. Okay. Now, the second thing, we try to create simple predicted set, okay? Something I can see very obviously. Then I apply rule number 1, predict in predict set. Rule number 1 say any token that appear as the leftmost symbol in the production rule of A, so any token is the leftmost. So any token that is my leftmost token. So this is the token, this is the token, this is the token. So this one is my predict set in the expression tails predict set. So this one go to here, this one go to here, this one go to here, and these two go to here. This is the predict set of the factor. So when I have this factor, I'm going to see these two tokens. Either it's a number or it's a left parenthesis. Okay, that's a application for the first rule for predict set. The second one, this is the second one. Apply the rule 1 for follow set, and then the first one for follow set is any token that immediately follow A on any right hand side of the production rule. That's my follow set. So initially you need to insert the $sign in because that is the end of the program. So the end of the program sign is the top level starting symbols follow set. That's the default one. You need to insert it there. And second, I have an expression. Anything immediately follow me, anything immediately follow me, and that is a token. I will include it. So I put stop and right parentheses in the follow set of the expression. After that, I apply the follow set rule number 3. The number 3 said I'm A. I'm the right hand side, the most right hand side non-terminal for a production rule for B. So B's follow set will be my follow set. So B is expression, its follow set is my follow set. So copy whatever B's follow set to my follow set. So put this through here. So this becomes the follow set for expression tail. And then the next one, the predict set. If A belongs to empty production set, every token in A will be my predict set. So actually, I copy my own follow set into my predict set because I am in the empty production set. So just copy this to here. So you can see right now we are processing follow set one by one. Either it's in follow set or it can be copied to predict set. We are doing this one by one from top down. Okay. The next one, applying the follow set rule. Follow set rule 2 is any non-terminal B immediately follow A on any right hand side production. So then we have what? So anything in the predict set of B right now is this expression tail. So anything that this will predict, that's the first symbol you will see. That's the first token you will see. Will be my follow set. I'm A. I'm A. And I'm turn. Okay, so expression tails predict set will be the follow set for turn. So this one copy to this, append to it to here. Okay. The next one, rule number 3. For follow set rule number 3, it will be I'm the rightmost non-terminal, and B's follow set is my follow set. So copy from terms follow set to term tails follow set. The next one, predict number 3, predict number 3. Okay, this one is I am a empty string. I can expand to empty string. So all of my follow set is my predict set. So just copy this over to here. The next one, follow set rule number 2. Anything in this term tails predict set will be the S factors follow set and also will be factors follow set. So right now we apply this same rule into 2 situations. So copy this to here and here. So this follow set now is being done already. The next one is apply rule number 2 for predict set. Rule for number 2 for predict set. That would be every non-terminal B appear as the leftmost symbol in predict set in the production rule. So right here, this one the leftmost non-terminal in the production rule for expression, and then everything in the predict set of B, predict set of B that is the factor. Okay, that's the that's the terms predict set will be the predict set of expression. So anything in the predict set of the term will be the set for expression. So right here, let's start it from the lowest part. So anything in this predict set of factor will be in the predict set of S factor. So from here, you copy this, append to here, and then the next one, S factors predict set will be part of the terms predict set. So copy from here to here, and then anything in terms follow set, predict set will be in the expressions predict set. So from term, copy to here, and then the last one from expressions predict set, copy to this starting symbols predict set. So now we finish the whole table. We have the complete EPS, predict set, and follow set. And taking the set element, first is easy to be found. First set, just trace down the tree, you will be able to find it, okay? So that's not hard. Now, we build the follow set and predict set. For the use of top-down parsing, every symbol in EPS and in any predict set is tagged with the empty production rule. Every non-terminal in EPS is tagged with the rule that gives the epsilon production for that non-terminal. Every token in prediction set A that was added from rule 1, rule 2 from the previous slides, prediction set definition is tagged with the production rule A that brought to the token. Every token in prediction set A was added from rule 3 on this slice is tagged with the tag A, with the tag on A in empty set. That is the rule give the epsilon production of A. And okay, anyway, this is not very important. Let's go to here. So right now, here is the algorithm to calculate the EPS and calculate the follow set and calculate the prediction set for whatever the calculator language we talk about. But as you can see here is a lot of math. I believe this is hard to understand anyway. Let's move on. So this one is the obvious fact about LL1 calculator grammar. So it is actually talking about those set related issue. So which set is what? This is about the facts. So we don't want to go too detail into here. And eventually, after calculation, you got first set, follow set, and pretty set for the calculated language. So this pretty much is the same method that I just show you. Using the method we use, we'll be able to calculate all of this. And the textbook actually is quite busy on this, but it's hard to understand anyway. So predict ambiguity. If any token belongs to the predict set of more than one production rule with the same left-hand side, then the grammar is not LL1. That means if you have a left-hand side terminal, non-terminal, and they are 2 or 3 different tokens, three different tokens in the same left-hand side non-terminal, then the grammar is not LL1. Actually, this just means the common prefix stuff. Okay, a conflict can arise if the same token begin more than one left right-hand side. This is left recursive or common factor things. And it can begin on the other side. Okay, this is not important. It's just talking about a common prefix. Now, wait. Okay, so right here, actually, I talk about how to create a table for the LL family. So that's how basically by using that, I build up this 4 set for the table used in the parser for LL family. And then, and that table is used here. So whatever table we described so far is the table being put over here for the prediction algorithm we use here. And this will complete the building of the LL parser with the right table. And the table is described as here. And that finish our discussion on the LL parsing. The next thing I would like to discuss is the LR parsing. Let me check what you're doing. So, are you okay with LL? Okay, then let's move on the LR part. Left-right parsing, and actually this one is more important. It's a bottom-up parsing, and it is used for yak. So this one is and bison. So this is more important. LR family parsing is using the ship reduce method, and ship reduce we already talked about it in yak and bison discussion, because ship is to push thing into the stack. Reduce is pop up and then move up one level in the syntax tree. So this is described as LR parsing. There are a number of variants. Hence, the use of the term LR family, that is, the variants are the SLR, LR0, LR1, and also LALR, those kind of stuff. They differ only in the generated table. So the main difference is also in the table. The algorithm and other things, they are the same. The L in LR predict the string is passed from left to right. R indicate the reverse of a right derivation is produced. So this one is the bottom up. Given the grammar, we want to develop a deterministic bottom up method for parsing legal strings described by the grammar as in the top-down parsing. So there's nothing special. We can do this with a table and driver. So let's look at it. These two charts give you a very important comparison about the grammars. Okay, any LL0 is part of the LR0. LL1 is part of LR1. LL2 are part of LLK are part of LRK. The reason is LL0 or LL1, this LL family, they don't have the left recursive, and they don't have the common prefix. And because if they don't have that, if you don't look at that, it's still a LR grammar. Anything can be passed by LL, can be passed by LR. So that's why any LL0 is part of the LR0. So this are apparent. So the LL1 algorithm we talked about actually will cover some part of the grammar for LR1, but not completely. So in the space of grammar, this purple one and the red one that actually are the commonly used grammar set for the compilers. So some compiler may use SR1 or LR1. Anything outside here, the complete context-free grammar, or this may have some grammar actually not built by any compiler at all. But these two are more popular. Either you are using the LL parser or the LL parser or LR parser. And the reason why anything outside here is not used is because in a previous lecture we talked about the time complexity, and a parser algorithm is a n-cube algorithm. So we try to use the linear time or somewhat above like n log n time, the checkable algorithm, to handle it. So the grammar need to be designed within this either red or the purple grammar in order to be used for compiler. So bottom-up parsing. A bottom-up parser works by maintaining a forest of partially completed subtree of the parse tree, which it joins together whenever it recognizes the symbol on the right-hand side of some production used in the rightmost deviation of the input string. So basically, because the parser is bottom up, so once you finish a certain parse tree, you need to maintain those parse tree, and then later you join them together. Okay, so that actually, let me show you the slides. Now actually it's talking about here. Once you finish some subtree, you need to maintain it, and later in upper stage, you actually join the tree together to build the AST, the syntax tree. That's what it's talking about. So because it's bottom up, so you need to keep track of it and build up the tree later. So that actually is achieved by the parse tree and parse stack and the value stack. Okay, in the Python or EL environment, and then you create a new internal node and make the root. This is ROOT of the joint together tree, the child of that node. So basically, those subtrees are becoming the sub node, the subtree for the new node. So we build up a higher level node to hold the subtrees. So like a table-driven LL parser, an LR parser use big loop, which it repeatedly inspect two-dimensional table. So every time we inspect a two-dimensional table that has the action and the action information and go-to state for the LR parsers. So unlike LL parser, however, the LR driver has a non-trivial state like DFA. Because in the LL parser, we have the what? We have the depth recursion issue. So right here, so the LL parser has a lot of trivial state, but LR parser is just like DFA. So it is actually very clearly defined. And in fact, the SLR family are using deterministic finite state machine to handle it. So the table is indexed by current token and the current state. So basically, it has just like a state, and then you have input token, you move on to the next state, something like that. So it's a very clear-cut deterministic finite state machine. It has a current state, and then you have a token, and you will move on to the next state, and that transition will not be ambiguous. Then so it will be one input token go to certain state. There will be no token, no two token going to the same state. They will not have one state and have one token and going into two states. No, nothing like that. So the state contains a record of what has seen so far. So those scenes are pushed into a state. So right here, this is a model for LR parser. So basically, we actually have some duo like the BNF written in Python environment, right? In Python environment, the left-hand side is the production duo, right-hand side is the action. So those actions are something we would like to generate some call, or we would like to do something. But right here, the action is similar. If you have the match the left-hand side duo, then we will do certain shift, reduce, accept, and error for different operations. And also, that duo will be used to go to certain finite state machine. And the parser will push the symbol for the state and the value into a step. Now we call it parse step. And actually, some program like the EX situation, the EX, the YY parse actually have a value stack as well. So this stack can be one stack or two stack. And those action rules and those action and the transition for the state will be put into a table. And this table can be constructed by LR0 method, SLR method, or LR1 method, or LALR method. These four different methods will create different table. So it all depends on what grammar you have and what sort of DFA you will create. So based on the grammar, construct the finite state machine, and then so that finite state machine come with different operations. So that's how we build a LR parser. And we are going to talk about how this whole thing works right now. And basically, we will be using this. Another grammar is expression, go to expression plus term, and then expression go to term, or expression go to term times factor, or expression go to factor, or expression go factor go to parenthesis expression, or factor go to ID. This set of grammar, and this set of grammar will create such a prediction table. I'm sorry, not prediction table. Or create such a parse table with action and go to. And this S is shift. So push things into step. the R will be reduced. That will pop up. So we will talk about this in the next lecture. Right here, we start to talk about the example. So the parser driver action, it has 4 operations or 4 actions. The first one is ship. So in the table, we have ship. Ship is indicated by S number entries in the table, and the number is a new state. So basically, you push something into the past stack, and then you go to the next state. The next state is the next state for the DFA or the final state machine. And then when we come to this entry in the table, we ship the current input symbol followed by the indicated new state to the stack. So let's go back to the state transition diagram. So right here, say right now if I am in state number 1, so current state is this. I see a plus sign, a token coming in. Then I will push the current state. I will push this current state and the token into the stack. And then I'll push in the current token and the next state into the stack. And I will go to the state 6. That's what it said. So right there, the S6, actually, we ship the current input symbol. That's the plus sign in that situation. And the new state is number 6 into the stack. Okay, that's what this ship is. For reduce is indicated by R number, and the number is the number of production. The top of the stack contains the right-hand side of a production duo. So right-hand side of production. So this actually number right here is the production duo. So what this means is actually right here, for example, right here, we in state 3, if we see a plus sign and then it say reduce 4, this 4 is production rule, means that I'm going to pop out something and then apply the rule number 4. Rule number 4 is term go to factor. So this number 4 means this rule, not a state transition. So that is this reduce. This R4 actually is the production rule that I'm going to apply. And then after that, you consult the go-to part of the table for the next state. So actually, the go-to part will depend on the current state, that you actually pop out, and then you find the current state and find the next state. We will see the example later. And then accept is indicated by the accept entry in the table. Once you see this, means that your parsing is completed. And if we go into the blank entry in the table, that indicate a syntax error. So right here, for some reason I go into this in state 1, but I see a parenthesis. That means I create the input file is wrong. The language cannot be accepted. So that is a compilation error. Okay, these are the 4 actions will be taken in the parse table. The next one is the driver algorithm. So I have an LR parser driver. Initially, I set the stack to be 0. Then I append a $ to the end of the input. That means the end of the program. Once I see it, and I will actually create an accept. Then actually is the end of the program. Or if action is an error, then I will stop. That means that my program is wrong. Other than that, I will go into here. For example, if currently I have this different thing in my state, and I have the remaining token coming in like this sequence. So I base on my current state and the input token, I use that, look at the table, and actually that table represent a characteristic finite state machine. This is the finite state machine. And then based on that finite state machine that being put into the table, I will decide whether I should push into the stack or I should pop it out. And actually I should go to next day, or I should apply a certain production rule that is actually, that production rule actually is on the left-hand side of the part 2 of the Python's file, something like that. And right here, let's look at one example. This example has this set and this parsing table we talk about. Now let's get started. If we have a input token string like this, A times B plus C, parentheses, then we start with the state 0. We start from state 0. And then state 0, we see an A that is an ID. So I have an ID. Let's say go to S5. S is to push. So then I push my ID in. That's this ID in. And then I also push the new state 5 into there. So that's the action of S5. And after that, I go to state 5 because that's my new state. In state 5, I will see a coming token of star, and this coming tokens of star will say reduce 6. So reduce actually is pop up. So I pop up this ID and 5, get it out. Both of them are pop out. After pop out, I apply rule number 6. At that time, I'm in state 0, that's my current state. So I apply this rule number 6. I am going back to my state 0, and I apply rule number 6. And rule number 6, the left-hand side is F, a factor. And then it suggests I should go to state number 3. Okay, then I push this left-hand side symbol non-terminal with the state 3 into the state. So my new state becomes 3 at this point. And then I go to state 3. And then at state 3, I see a star symbol. This star symbol had not been processed yet. It just precedes in the previous situation. I saw my rule is R4. So what I would do, that's reduce. When I reduce, I pop out F and 3. And then I need to apply my rule number 4. Rule number 4 says it's turned to factor. So actually the previous rule, I have ID, on top of it I have factor, and then now on top of it I have turn. So I pop out the F's and 3. Now I'm in state 0, and at the state 0, I see a terminal on the left-hand side. That's a terminal. I go to state 2. Then I go to state 2. So now I go into state 2. In state 2, actually in state 2, that's right here in state 2, actually I see a star. The star has not been processed yet because the previous 3 do I just do ID and then factor and then go up. There is a turn. So right here I see a star. When I see a star, it said that go to actually it's shift. Actually it's a shift and go to stage 7. So I push in my star and that star being consumed now. At this time it consumed the star. And then I push my 7, the new stage 7 over there, and I will go to this stage 7. At stage 7, I will see a parenthesis, left parenthesis, and that parenthesis I see is a shift and then stage 4, shift and then stage 4. I push in the parenthesis and I put in my new stage 4, and I go to stage 4, and then right here I will see an ID. Stage 4, I will go to stage 4, I see an ID. It say shift and 5, so I put in the ID and number 5. I go to stage 5. In stage 5, I actually see the ID has been pushed in, right? And then the next one, actually, I see a plus sign. In stage 5, I see a plus sign. Stage 5, I see a plus sign that go say reduce. So reduce, this got pop out. So it repeat the one we saw. So it's a pop out, and then it actually go R4 go R2. So eventually I come to this T2 again, because that one ID, then the plus sign had not been consumed yet. And in state 2, I see a R2 with the plus sign. So the R2 actually will use the rule 2 and pop out the plus sign, and then I see actually a plus sign. The plus sign is now being consumed, and C actually is the next thing will be seen right here. So actually you follow these different steps, and you will see one by one how the whole thing being processed. So at the end, you will see on the step number 19, you will see a dollar sign, and dollar sign at that time you are actually in state 1. In stage 1, you see a dollar sign, you will accept, and then the parsing completed. So basically, that's how this LR parser is working. And LR parser is based on the action and go-to table. It's based on the action and go-to table, and it will push in the data and the state into one state. But remember that in our EX or Python environment, we have 2 states, one pass stack and one value stack. And that value stack is pushing in those numbers and plus sign, those operators, ID and the operator being pushed into the value stack. And right here is one stack design. And that EX Python is a 2-stack design, but it actually functions similarly. So that's not a problem. Now let's go to there. And then we finish the LR example. The next thing we will do is look at the calculator example in our textbook. So canonical derivation, that is the LR derivation. We saw this in previous example. I won't repeat it, but this is the LR family. And button-up grammar for the calculator language. In our ID list example, no handle were found until the entire input have been shifted into the stack. So the ID example is the previous picture. in general, this will not be the case. So that won't be the general case. We can obtain one more realistic example for the calculator shown in 225. The version in figure 225 is preferable for bottom up for two reasons. And let's look at the figure 225. So the grammar has been rewritten from this 216 to 225. So 225 actually make it left recursive, and left recursive is good for LR family. It is bad for LL family. So LL1 grammar for the calculator language production have been numbered for reference in the future figure. So these are the dual that will be used in the future. And right here, first, it used left recursive production for the statement list. Left recursion allows the parser to collapse long statement list as it goes along, rather than waiting until the entire list on the stack and then collect it from the end. So basically, left recursion is good because you go down and then you actually being able to make the derivation more effectively instead of waiting until everything being pushed into the stack. Second, it used the left recursion production for expression and turn. This production captures left associativity while keeping an operator and its operands together in the same right-hand side. So basically, this just said that left recursion help the parser. And this cannot be done in the top-down grammar. And right here. Okay, now we are going to model a parser with LR items. We use this sum and the average program as an example. The key to success will be figured out when we have reached the end of the right-hand side. That is, when we have handle at the top of a parse stack. The trick is to keep track of the set of production we might be in middle of at a particular time, together with an indication of where in those production we might be. So basically, you need to know about what set of the production rule we have and where we are in the production rule. And by doing that, when we begin the execution, the entire stack is empty, and we are at the beginning of the production for the program. So basically, we will trace one by one to see how the action table and go-to table are created. So right here, we define a LR item, a production rule with the black square is called an item. So we have the rule right here, several different rules, and it will start it here. That's our black square. That represents the location on top of the stack. So currently we're starting from here. That the original item, program statement list, and double dollar sign is called the basis for the list. So this is the basis for the list. The additional item is called closure. So the rest of them are called closure. The list represents the initial state of the parser. So this is actually the initial state of the parser. And we shift and reduce the set of the item will change. So basically, this item will change because this location will move. It will move. When you move, you'll create different state and will also create different go-to and actions. But these are the rules we keep track of. So we know about the production rules, and also we will create different action and go-to commands. So let's look at an example. So right here, the operation for shift, reduce, and the shift and reduce. So three different action, and this is slightly different from the example I give. because the previous example has some problem. That's a simplified version. I try to show you. Right here, you can see that somewhere with this T2, actually this right here spend quite many push and pop. But actually there is a shift and reduce operator can actually make this faster. So that's why in this version that we are seeing right here, it has shift, reduce, and shift and reduce. So S, R, and B, 3 kind of action. And the previous example we used has only 2. But we use that example to show you how shift, reduce are done. And it can be simplified like this textbook situation. So in the beginning, we actually starting from the read token. So we have a statement, and we actually see a starting location right here. We see a read. So we push in this statement and read into the stack, right? That's the first point. And then we read A, so we put A into there as well. And A is an ID. After that, actually, we see the end of the statement. So we see the end of the statement. Then actually, we will pop out the read and A and create a parse tree like this. Okay, and then we will transition to actually we are finishing. Actually, we finish this statement. We go back to this statement is done, and then we go back to here, and then we switch to state 2. So by the method we talked about there, actually for each state and different location, we actually will come out with this different state and the rule, and will come out with the action and go to part created for the LR parser. So right here is a complete state and related to rule table in figure 2.26. And that actually will give you a state and the coming token and the next state. This kind of, so use the graph to generate the go-to section of the parse table. So you will use that rule. You use this big table and what you are going to process, and the new state you are going to, by using such method, you create a different state number, and then you also associate with the shift and reduce operation. Then you will construct such a state machine, and that state machine will be used to generate a go-to section for the parse table, and that actually will be used to construct the final state transition table and the operation table right here. So this is the go action and go-to table for our calculator language in the SLR algorithm. But right here, remember it has shift, reduce, and shift and reduce, 3 kind of operation actions. That's slightly different from the example I gave. But the example I gave is simpler, and this one is more complicated. And also, this one is faster because it combines the shift and reduce. And then here is a SLR parser. So this parser actually would have the table, this is a table, the symbol, the production rule number, and the symbol and the right-hand side integer. And also there's an action list about action and new state and production rule. So actually this is what is used to construct the action and go-to table. The result of action and go-to table is right here. And your driver program is similar to the LL parser. So basically, you check the current symbol and the current state, and then you, if it is the symbol that you would expect, actually you will return. I'm sorry, if the current state is the accept symbol, then you have success. If this is wrong, then it will create error. So this algorithm actually is the same as this algorithm, and slightly different from the LL1. So it's trying to check the accept and error condition and trying to find the action and shift and reduce actions. So that algorithm is actually this algorithm. You push in the state, and then you use the current state, and use that. You try to check if it is on top of it, and then you check whether the symbol is actually correct or not, and then you decided whether to go shift reduce or create pass error. So that this one is implementing similar algorithm than the one I showed, and actually this is the SLR parsing with the shift reduce and shift reduce for the sum and average program. So this whole thing is similar to this, except that it used the SL algorithm in the textbook. So I use a simpler example to show you, but here is more complicated described in the textbook. And it doesn't show the steps by step. This is quite complicated. Now, the other topic for LR parsers. LR parsing variant. LR0 were created, no look ahead used to create them. And we did consider the next input symbol when creating the table. If no look ahead is used to create a table, then the parser is called LR parser, but this is not really very useful. And LR table is typically for typical programming language when the language is very massive. And that table is actually very big. And SLR1 parser recognizes many but not all. So SLR is a simplified version, but there may be some construct too complicated, cannot be handled by it. But if your language is not that complicated, then you can use the SLR algorithm. Or if those typical one you handle by heuristic, you can have a variant for SLR to handle some programming language as well. Another typical one of a parser is the LALR1. It recognizes almost as many constructs as LR1, so it's better than SLR, but it is faster. It's constructed by first constructing the LR1 items and states, and then merging many of them. So this one is very too big, and it's trying to merge most of them. And when two states were the same, except the look ahead table, they will be merged. So LALR1 is simplified from ALR. The first look ahead means look ahead token is added to them. Okay, so basically the driver program is the same. Tables are generated differently, and grammar actually also the same for these, for the LR, SLR, and LALR. It's only the table that make the difference. The grammar are different. They have, let me see. The grammar for SLR is different, but simpler members of the parser, LR0, SLR1, and LALR1 use the same automata. So these three are sharing the same grammar, but LR, the complete LR is different. Full LR parser use a machine with most grammars. So everything is put in there with large number of states. The difference between the algorithm lie in how they deal with the states and how they contain the shift reduce conflict. So these three actually have the same finite state machine. The grammar is the same, and the full one is different. So LR, full LR is different from this simplified one. And simplified one need to make some restriction on the grammar, but these three have the same grammar. And bottom-up parsing table, these three have different parsing table but share the same finite state machine. And these three parse execute a loop in which repeatedly inspect the two-dimensional table to find out what action to take. Instead of using the current input and the top of state non-terminal to index into the table, and this one is used for LR. LR, this one is the top of the state non-terminal and the input token. That's used for LL family. LR use the current token and current state. And this operation, we talked about it already. So that's for shift, reduce, and finding the next step, next state, either by the S number or by the go-to section. Handling epsilon production. The careful reader may notice that the grammar in figure 2.25, in addition to use the left recursion rule for statement list expression and term, is different from figure 2.16 in one way. It defines statement list to be a sequence of one or more statements, and rather than 0 or more. And actually, this one can be replaced by this as well, because some of the programs do have empty statement and empty program. So note that it does in general make sense to have a empty statement list. In calculator language, it simply permit empty program. So some program that permit the empty program for that language need to handle this epsilon production. You need to allow a complete empty program. And in reality, some people do write a subroutine or a module totally empty, and the compiler should still be handling. So here talk about how to handle the epsilon production. So in Duo and the table construction, if we look at the characteristic of finite state machine for calculator language, we discover that state 0 is the only state that need to be changed in order to allow empty statement list. So basically, you change list into this, and this is equivalent to this, or simply this. So basically, try to accommodate the empty string. The entire state is then like this. It will be changed like this. So adding this statement that would be allowing the empty string. So the look ahead item for this is in the follow set for this, which is the end mark this. So this end mark will be added into the follow set of the statement list, would allow the empty program, and SS $sign sin does not appear in the look ahead for any other item in this state. Our grammar is still SLR1. So anyway, right here is trying to help to handle the empty string and make a program to allow the empty program. Okay, now we finish the LR parsing and LL parsing, and let's review the whole chapter. In this whole chapter, basically, we talk about regular expression, context-free grammar. We talk about parsing, and we cover the yak and back for the lexical analyzer and the Bison for the parser design, and it take the lexical rule from the regular expression definition, and it also take the grammar rule for context-free grammar for a language. And then we demo several simple demo program to create a YYLex and YYParse program, and this actually is used for compiler design. And then after that, we discuss the LL family parser. Actually, that is used the prediction set to create a prediction table. And also we discuss the recursive descent algorithm. And at last, we discuss the LR parser that's based on the exchange and go-to type of parse table. And this is what we talk about. And actually, we have these slides before. It basically shows you how to convert from source code to tokens to syntax tree and then to machine code or some intermediate code. And then we actually see this using the rule and use Python or Flex to create the .c file, the header file, and your YYLex program. And then you compile together to create a calculator. And right here, showing you how Flex take in the latex file to create lex.yy.c and how the lex file work to create token string. And then Flex is a fast lexical analyzer. We talked about this already. And Bison and yak combined with the lex or Flex can help you to do compilation, building of the compiler. And scanner parser interaction, we talk about this. I will omit it. This one, same thing, we talked about it already. And YYParse basically is using a LR family. Actually is close to SLR algorithm to build this, generate a parser for you. And it repeatedly call YYLex until it is done. If there is an error, then you will call YY error. That actually is the error we see. The YY error is handling what? Handling this parse error for you. That's the YY error. And YYWrap is when the whole thing been done, we actually return one. Actually, this number is something you will see in your YYWrap. And YYWrap actually is YYWrap actually handling if the whole program finish correctly, you will actually use the YY wrap. Okay. And then this is YAC format. We've done this already. And this is one Python grammar rule. So, so in the YAC or Python environment, we started from a grammar. Those kind of grammar we saw it today for the LR grammar, and then we combine. Actually need to design it and then put into the YAC format. Now actually here is a semicolon, not an arrow. I'm sorry, here should be a column. And then you put down the rule like this. And then that actually you put down your code to be handled for the action part. And eventually you can run it on GCC environment. So actually now I told you how to actually build the regular expression file for different application, and also the token generation, and also the possible parsing. And that these three different tools is very useful for many applications. And also today we talk about the design of different parsers. And in the next two chapter 3, we talk about the type definition and type checking. Chapter 4 about semantic generation. These two chapters all based on chapter 2. So chapter 2 is the most important part in our course. So I will conclude my talk today, and then we will move on next week into the semantic checking and semantic analysis. That's also part of the parser stage. Thank you. Bye. Let me go back to check. Actually, let me check whether Miguel had some issue or not. Hello. And chapter 2 is actually quite important, you know, and because chapter 2, 3, 4 are in this compiler issue, and then after that, chapter 5 is the code generation, and beyond that is all just discussing some data structure, program structure, those type of things. Most of people may know that it's just define, actually discuss in more general sense for different languages. Other than that, it's not as difficult as the chapter 2, 3, 4, and maybe 5. This fun part are more difficult. Okay, then that's it for today. Bye.